Have you ever paused to wonder how machines, even these incredibly powerful ones processing mountains of data, could ever really grasp the meaning behind a simple word, like apple, or, the concept of red?
It's definitely more complex than just crunching numbers or spotting patterns, isn't it?
Absolutely. Welcome to the deep dive. Today we're looking at something pretty fundamental in computer science and AI. It's one of the grand challenges, really, in both artificial intelligence and cognitive science, the symbol grounding problem.
Mm.
At its core, it's asking, how can a system, like an AI, genuinely understand its internal symbols? How does it get beyond just manipulating them like abstract tokens?
Right. And our mission for this deep dive is really to explore that fundamental problem. We'll look at how it was first defined, some of the early attempts to solve it, and then get into some more modern ideas, especially this framework called conceptual spaces. So you'll hopefully get a good handle on the layers of meaning and perception that seem pretty crucial if we want truly intelligent systems. We'll look at the sources that define the problem, analyze some solutions, and really dive into how a kind of geometric approach might hold the key.
A geometric approach. Interesting. Okay, let's unpack this problem a bit more then. So imagine a sophisticated computer program. It can process words like cat or dog easily, right?
Sure. Modern systems are amazing at that.
They can follow instructions, generate incredibly coherent text about cats and dogs, but does it truly know what a cat or a dog actually is in the real world?
Does it get the catness or dogness?
Exactly. Does it understand, the feeling of soft fur, or that distinctive meow sound, or how a dog's tail wags when it's happy? This gap, this disconnect between the symbols inside the system and what they refer to out here, that's the symbol grounding problem, right? The SGP.
That's the core challenge, precisely. The SGP, and it was cognitive scientist Stephen Harnad who really articulated this, well, it's all about how those internal symbols get their meaning without needing an external interpreter. Without a human programmer constantly whispering in the AI's ear, that means this.
Right, it needs to figure it out itself.
Exactly. And Harnad proposed a really insightful three-stage process for how a system might achieve this grounding. First up is iconization.
Iconization.
Yeah. Think about raw sensory input, like the actual light waves hitting your eyes, or sound vibrations. This stage is about transforming that continuous sensory stuff into distinct iconic representations. Basically, direct patterns of data the system perceives.
Okay, so like processing the raw pixels from a camera feed?
Pretty much, yeah.
Yep.
A direct representation. Then from those iconic patterns, we get to categorization. This is where the system starts grouping similar iconic representations together into categories.
So putting all the cat-like patterns in one box?
Exactly. And these categories effectively become the names for the things those symbols refer to. And finally, the third stage is naming. That's where these established categories get explicitly linked to the actual symbols the system uses, like the word cat gets tied to that group of cat-like patterns.
Okay, so icon, category, name. It seems logical. So Harnad's idea was this hybrid model then, using connectionist networks for the pattern matching and categorization part.
Neural networks are great at that.
And then a traditional symbolic system manipulates those symbols once they have meaning. That sounds like a decent start. But were there criticisms? Did it really solve that external interpreter issue you mentioned?
That's a really good question. Because despite being hugely influential, some early criticisms, folks like Christensen and Chater pointed out something important. They argued that even with this hybrid model, Harnad's initial solution still seemed to need an external supervisor. Yeah, something or someone still had to kind of check and validate whether the network's self-organized categories were actually correct, which suggested the grounding was still a bit, well, extrinsic, not fully internal to the system.
The meaning was still being given rather than truly learned from the ground up. Okay.
Precisely.
That makes sense. If it still needs that human stamp of approval, it's not really independent understanding. So how did researchers try to get past that need for external supervision?
One significant push came from researchers like Ron Sun, working with his Clarion cognitive architecture. He focused on this idea of intrinsic intentionality.
Intrinsic intentionality.
Yeah, the idea that the system's goals and understanding should come from within. He proposed a two-level learning process. The first level was all about the agent having direct interaction with its environment, just encoding its experiences raw. Think of a robot bumping into things, learning the consequences.
Learning by doing, essentially.
Exactly. And then the second level would work on elaborating more abstract conceptual representations from that raw first-level data. The goal was to figure out how to behave optimally in the world based on those experiences. The powerful idea here was that the AI's intentionality, its understanding, could maybe derive purely from these direct interactions. No need for a human to predefine all the semantic meanings.
Okay, that definitely sounds like a step towards more autonomy, but
Mm-hmm.
did it completely crack it? Was it really free of all external influence, or did this kind of push lead somewhere else, maybe towards embodied AI?
You're spot on. It was a great step, but critics still argue that even Sun's approach sort of implicitly assumes some kind of semantic framework, like maybe a fitness formula, guiding the agent's learning, which ultimately still originated from an external source, the programmer usually.
Mm.
So this persistent challenge, trying to get truly intrinsic grounding, did fuel the rise of embodied cognitive science. This really shifted the focus. The symbol grounding problem became the physical symbol grounding problem, the PHSGP. The emphasis moved to the idea that genuine understanding isn't just abstract thought. It's deeply tied to having a body and interacting physically with the world.
So the sensors, the actuators, the whole physical presence becomes critical.
Absolutely key. And a great example of putting this into practice is the work of Paul Vogt. He did some really clever work connecting Harnad's ideas with situated robotics, robots acting in real environments, and also with Charles Peirce's semiotic definition of symbols.
Semiotics, how signs create meaning.
Exactly. In Peirce's view, a symbol isn't just a label, it's more like a triad. It has a form, it's the physical shape, the sound waves that have a meaning, the semantic content.
Mm.
And crucially, it has a referent, the actual thing or event out there in the world that the symbol points to.
Right, that distinction between the internal meaning and the external thing is vital.
Absolutely. And to achieve this physical grounding, Vogt and others heavily used something called the guess game, which was developed initially by Lucas Steels and Vogt himself.
The guess game.
Yeah, picture this. Two robots in a shared space. One acts as the speaker. It looks at an object, perceives it, and comes up with a symbol, maybe just a random noise initially. The other robot, the hearer, has to try and guess which object the speaker is talking about.
Ah, okay. Trial and error.
Lots of it. Through repeated rounds and, crucially, using sensoromotor feedback like the hearer maybe points or moves towards its guess, and the speaker gives feedback based on whether it's right to the friend. They gradually, collaboratively, develop a shared language. They converge on symbols that reliably refer to objects in their shared perception.
So they're building their own grounded vocabulary just through interaction.
Precisely. They autonomously ground their symbols in their own sensoromotor activities in what they can see and do. It's almost like watching two toddlers learn words by pointing and babbling until they agree that this noise means that block. They build shared reality from scratch.
That's a fascinating picture. So, okay, pure symbols aren't enough. Even embodied action still seems to have some hurdles. Is there a framework that really tries to bridge this gap, something that aims for, genuine understanding of what things are?
Well, this is where the conceptual spaces approach really comes into its own.
Huh.
And it's gaining a lot of traction in AI and computer science because it offers a very elegant potential solution.
Okay.
This framework, and Peter Gardenfors is the name most associated with developing it, basically suggests that AI needs three distinct representational layers to build up meaning.
3 layers, like building blocks.
Kind of, yeah. At the very bottom, you've got the sub-symbolic layer. That's just the raw perceptual data. Think pixels from a camera, raw audio waveforms, just the unprocessed input.
Got it, raw data.
Then above that, there's this crucial intermediate layer, the conceptual layer. Here, knowledge isn't symbols, it's represented geometrically as conceptual spaces. And the really key thing is that the dimensions of these spaces, like axes on a graph, are directly grounded in those sub-symbolic processes. They emerge from the raw data.
Okay, so a middle layer based on geometry derived from perception, and the top layer.
The top layer is the symbolic layer. That's where you find your traditional AI, symbols, words, language, the abstract concepts we usually deal with.
Ah, so this conceptual layer is the bridge. It connects the abstract symbols at the top to the raw perception at the bottom.
Spot on. That's the core idea. It provides that missing link. Symbols from the symbolic layer aren't just floating free, they get their meaning indirectly by being grounded in sub-symbolic perception through this intermediate conceptual layer.
Can you give an example? Like, how would red work?
Sure, so red isn't just an arbitrary label in the symbolic system. In the conceptual spaces framework, it maps to a specific well-defined region within a conceptual space for color. This space might have dimensions like hue, saturation, and brightness, derived from how we actually perceive light. The concept red corresponds to a particular volume or area in that space.
A geometric region. And you mentioned convex regions earlier.
Yeah, often concepts are assumed to correspond to convex regions. What that means basically is if you take any 2 points inside the red region in this color space, any point on the straight line directly connecting them is also considered red. It helps keep concepts coherent and reflects our intuition that categories often group similar things together smoothly.
That makes intuitive sense. But real-world concepts aren't always so clear-cut, are they? What about fuzzy boundaries?
Exactly, and that's another strength. Conceptual spaces handle fuzzy membership naturally. Think about a color like teal. Is it blue? Is it green? It's kind of both. This framework allows for that ambiguity. An input might fall near the boundary of the blue region and the green region, and the system can represent it as having a certain degree of membership in both. It reflects the nuances of perception.
Okay, and it doesn't just represent concepts, it could operate on them.
Yes, definitely. The framework supports various cognitive operations that allow the system to create new concepts from existing ones, much like we do.
Like what?
Well, think about intersection. You could define a concept like green banana. How? By finding the intersection, the overlap, between the region representing green in the color space and the region representing banana in maybe a shape or taste space. It's not just stringing words together, it's a geometric operation that combines meanings.
That's powerful, combining concepts visually almost.
It is. Or take union. You could create a broader category like citrus fruit by taking the union of the regions for orange and lemon. It allows the AI to synthesize new, more abstract concepts for more specific ones. There are other operations too, like projecting onto subspaces or cutting spaces along dimensions. It provides a rich toolkit for conceptual manipulation.
What really strikes me here is how this intermediate conceptual layer seems to offer real advantages. It's not just symbolic, not just sub-symbolic, but this bridge between them.
Exactly.
And it gives you dimensions that are potentially interpretable, right? Grounded in perception. Plus, these intuitive ideas like similarity, things closer together in the space, are more similar and even conceptual betweenness, something being halfway between two other concepts.
Right. It moves towards AI that's potentially more understandable, more explainable, because its internal representations have this structure that mirrors in some ways our own cognitive structure.
Okay, so if this geometric conceptual layer is so promising, the big question is, how do we actually create these spaces for an AI? How do we ground their dimensions in the real world?
Good question. There are basically two main approaches people use. One relies heavily on human psychology. It's called multidimensional scaling, or MDS.
MDS, okay.
What you do here is collect similarity judgments from humans. You show people pairs of things, say different kinds of fruit, and ask them, how similar are these two? You get lots of these ratings. MDS is then a set of statistical techniques that takes all these pairwise dissimilarity ratings and figures out a low-dimensional spatial map, where the distances between the points representing the fruits reflect those perceived dissimilarities.
So if people rate apples and pears as quite similar, they'll end up close together in this MDS space.
Exactly. And if they rate apples and bananas as very dissimilar, they'll be far apart. The big advantage here is strong psychological grounding. The space reflects human perception.
But I can see a potential downside. What if the AI encounters a fruit that wasn't in the original human study?
Precisely the limitation. MDS typically doesn't generalize well to completely novel inputs. It creates a map of the things you studied, but can't easily place new things onto it.
So what's the alternative?
The other major approach uses machine learning, specifically artificial neural networks, ANNs, often under the banner of representation learning.
Ah, deep learning territory.
Right. ANNs can be trained to learn mapping functions directly from raw inputs like images of fruit to points in some kind of similarity space. They learn the representation. The huge advantage here is generalization. Once trained, the network can process novel inputs, new fruit images it's never seen before, and place them into the learned space.
Okay, that solves the generalization problem, but are the dimensions the network learns meaningful? Can we look inside and understand why it put two fruits close together?
That's the challenge with pure AN approaches sometimes. The dimensions learned by the network might capture similarity really well, but they aren't always easily interpretable by humans. We might not be able to point to one dimension and say, that's the sweetness axis, or that's the roundness axis. It can be a bit of a black box.
So it feels like we want the psychological validity of MDS, but the generalization power of ANNs. Can we combine them?
Exactly. And that's where the really exciting hybrid approaches come in. The idea is to get the best of both worlds.
How does that work?
You start by using MDS with human similarity ratings to create that psychologically grounded target space. This is your ground truth for what similarity should look like. Then you train a neural network, not just to cluster inputs, but specifically to map raw stimuli into this predefined, psychologically plausible MDS space.
Ah, I see. So the network learns to embed things in a space that already makes sense to us.
Precisely. The training goal for the network becomes, take this image, process it, and output coordinates that are as close as possible to the coordinates that MDS assigned based on human judgments. This way, you hopefully get a system that's both psychologically valid and can generalize to new inputs.
That sounds very promising. And does this conceptual spaces idea also tell us anything about how AI might learn concepts from scratch?
Yes, it definitely informs concept learning. For example, in unsupervised learning, algorithms inspired by these ideas, things like cobweb, art, or sustain, can discover conceptual regions automatically. They look at unlabeled data points, group them based on similarity in some feature space, which could be a conceptual space, and form clusters that represent potential concepts, sometimes even hierarchical structures or prototypes.
So finding patterns without being told what they are.
Right. And maybe even more compellingly, think back to those language games that we mentioned earlier.
The robots talking to each other.
Exactly. Those simulations show how populations of agents, starting with just perceptual input and the ability to interact, can converge on shared vocabularies and shared conceptualizations. They might play guessing games about colors, for instance. Using something like the CIE Lab color space, which is designed to be perceptually uniform, agents can learn to carve up that continuous space into discrete color categories and agree on names for them purely through interaction. They align their internal conceptual spaces.
It's like they're collectively building their understanding of the world. Still, even with these hybrid methods and language games, ensuring those learned dimensions, especially from the ANNs, are genuinely interpretable. That feels like an ongoing challenge, doesn't it?
Oh, absolutely. It remains a significant hurdle, especially as models get bigger and more complex. Making sure we can understand how the AI is representing concepts, not just that it can represent them, is crucial for building trust and for explainable AI, XAI.
Right. So wrapping this up, our deep dive into the symbol grounding problem really shows it's far more than just a philosophical thought experiment. It's a core engineering challenge in computer science and AI research.
Definitely. It's been driving research for decades.
From Harnad's initial framing and those early struggles with keeping the grounding internal, all the way to this sophisticated conceptual spaces framework, the goal remains the same. Bridge that fundamental gap between abstract symbols and concrete perceived reality.
And what I find really compelling is how this research is trying to model something deeply human. How we understand meaning through our senses, through interaction, through this almost geometric intuition we have about concepts. Modeling that seems key to creating AI that feels more intuitive, maybe more understandable.
It's not just about more data or bigger processors.
No, it's about potentially giving machines something akin to a geometric, cognitively plausible sense of the world, a different kind of intelligence.
So here's a final thought to leave you with. If an AI could genuinely perceive concepts geometrically, sharing that kind of intuitive grasp of meaning that conceptual spaces suggest, how might that change our own understanding of thought? And perhaps more practically, what new levels of collaboration could we unlock with machines that don't just process symbols but truly seem to understand their meaning in a way we recognize?